Hello, I'm Thomas. I'm a lecturer in mathematics here at the University of Leeds. And in this podcast, I want to tell you about Taylor series of functions. What I want to do is I want to show you how you can compute a Taylor series for a function using an example. And then I want to briefly discuss some applications of Taylor series. Now, let us start with some motivation for the topic. Let's assume you have a very complicated function and you want to calculate loads of values of this function for different values of x, like the function given on the slide, f of x. These days, of course, you can just use the computer or your calculator and type it in, and then you get the answer immediately. But let's assume we don't have calculators or computers. Then a function like f is very difficult to compute, I'm sure you appreciate. And in fact, the theory of Taylor series goes back to the 18th and 19th century and was developed then. And obviously then mathematicians or people didn't have computers, and so they had to think of different ways to compute values of functions. Now, one possibility is to approximate the function f by simpler functions. So instead of looking at the complicated functions, we choose simpler functions which behave very similarly to f, and we compute values of the simpler functions. And what are good candidates for simpler functions? Well, for example, polynomials. Think of a polynomial like x cubed minus 5x plus 2. All you need to do to compute values of this polynomial is you have to multiply numbers and you have to add numbers. And that's quite easy to do. There are many different ways and methods in which you can approximate functions using polynomials. In this podcast, I want to talk about Taylor polynomials and Taylor series. These polynomials can be used to approximate a function near a certain point, in a small interval around a certain point, x is equal to a. Now here's an example, and this is the example I want to use throughout this podcast to show you how a Taylor polynomial and Taylor series can be computed. The function is a lot simpler than the one on the other slide. It's just f of x is log of x, so the logarithm, or if you like, ln x, depending on what you prefer. On the right-hand side, you can see a graph of the function in blue. And like I said, we only want to approximate this function near a certain point. And here in this example, I choose the point to be x is equal to 1. Now, the logarithm of 1 is, of course, 0. And so you see we have the point 1, 0 in the graph, and we want to approximate the function using polynomials. So we want to approximate the logarithm of x near x is equal to 1. Now, we want to use polynomials, and the simplest choice of a polynomial is just a linear function. Y is a times x plus b, for example. You will know that a linear function gives us a straight line on our graph, so we want to approximate the graph of the logarithm using a straight line. And then you hopefully know that the best choice for this is the tangent. So what is the equation for the tangent? Well, the tangent is the straight line that touches the graph of f at the point 1, 0, and it has the same slope as the graph of f. The slope of the graph of f at the point 1, 0 is given by the derivative of f at this point. So you see the equation for the tangent. Y is the function value f of 1, so the logarithm of 1, plus the derivative f prime of 1 times x minus 1. So if we set x is equal to 1 in this formula, then y is f of 1, just like we want it to be. And the slope is f prime of 1 times x, so it is the same slope as the function f. Of course, we can compute this. We have to compute f of 1 and f prime of 1. Well, f of 1 is very simple. We already did this. That's 0. And let us differentiate the function f. If we differentiate the logarithm, we get 1 over x. And 1 over x at the point x is equal to 1 is simply 1. So the equation for the tangent is simply y is x minus 1. Let's have a look at what it looks like. It is a straight line that touches the graph of f at the point 1, 0. And it has the same slope as the graph. So that's very easy. But now, of course, we can continue. We use the very simple polynomial, in fact, the probably easiest that is available, but we can use polynomials involving x squared and x cubed. And I want to do this step by step in the following. So let's start with a polynomial that has terms x squared in it. If you look at the formula, I've started with a very general form of a quadratic polynomial. T2 of x is a naught plus a1 times x minus 1 plus a2 times x minus 1 squared. The reason why I'm using x minus 1 rather than only x will become clear very soon. We have got three coefficients in this polynomial, a0, a1, and a2, which we can determine. And now let's just think back to the tangent. We determined the tangent because it has the same function value and it has the same slope. Now for our quadratic polynomial, we can also require that it has the same second derivative as f at the point x is equal to 1. This gives us three conditions, and from these three conditions we can determine the three coefficients. Well, we can do this rather easily. Let's start with the function value. At x is equal to 1, the value of t2 of x is simply a0. So we want a0 to be f of 1. If we differentiate, then a0 goes away, it becomes 0. The derivative of t2 of x is a1 plus 2 times a2 times x minus 1. If we set x equal to 1 again, then we're only left with a1. So we have our equation for a1. This must be equal to f prime of 1. And we already know these two equations because these are the equations that we use to determine the tangent. And now we have an additional equation because we have an x squared term in our polynomial. We want the second derivative of t2 to be the same as the second derivative of f. If we differentiate t2 twice, so the first two terms go away because they don't have any x squared terms in them. If we look at the third term, a2 times x minus 1 squared, if we differentiate it once, then we get 2 times a2 times x minus 1. If we differentiate it again, we just get 2 times a2. And we want this to be equal to the second derivative of the function f at x equal to 1. So 2 times a2 is f second derivative, or double prime, at 1. And now I just sub in these values for the coefficients into the equation, and I get the equation for t2 of x. So let's compute these values for the function f of x is log of x. We already know the value of f at the point x is equal to 1, that is 0. We already know the derivative, it's 1, because we computed this for the tangent. So the only thing we actually now have to compute is the second derivative of the function at x is equal to 1. Second derivative of the logarithm is the first derivative of 1 over x, because 1 over x is the first derivative, and so we get minus 1 over x squared. If we sub in x is equal to 1 into this formula, we find that the second derivative at x is equal to 1 of f is minus 1. So our polynomial is given at the bottom. Remember that we have to divide the second derivative by 2 from the formula on the previous slide. And here's what it looks like. In this slide you see again the graph of f as a blue curve. You also see the tangent as a light gray curve. And now I've also included the parabola described by our t2 polynomial. And if you compare the tangent to the parabola, you see that the parabola already does a pretty good job at approximating our function near the point. You see, if we move away further from the point, then the approximation gets a bit worse, but very close to the point, it does a pretty good job. So we've done a linear polynomial, we've done a quadratic polynomial. Let's move on to a cubic polynomial. Let's do it again in a slightly general way, first of all. I'm starting with a very general cubic polynomial, t3. So it's a0 plus a1 times x minus 1 plus a2 times x minus 1 squared plus a3 x minus 1 cubed. And we want to determine the four coefficients now, a0 to a3. What conditions do we have? Well, for the tangent, we wanted that the function value and the first derivative agree. For our quadratic polynomial, we wanted that function value, first and second derivative agree. And now we have an additional term, so now we can also demand that the third derivative of our polynomial agrees with the third derivative of f. We've already gone through the first three stages, so we can now only concentrate on the last coefficient, a3. In order to determine this coefficient, we have to differentiate t3 3 times. If you do this, you get 6 times a3. And we want this to be equal to f third derivative at 1. So a3 is just the third derivative divided by 6. The formula for t3 is given at the bottom of the screen. And you see it's the same scheme again. Right? The first three terms agree with the quadratic polynomial. The first two terms are just the tangent equation. And now we've got the additional term, the third derivative of f at the point x is equal to 1 divided by 6 times x minus 1 cubed. At the very bottom, I'm rewriting this slightly differently using factorials. I write 2 factorial instead of 2, and I write 3 factorial, so 3 times 2 times 1 instead of 6. It will become clear why I'm doing this in a moment. So let us have a look at what T3 looks like when we put it on our graph. Well, we need to compute the third derivative of the logarithm. That's the derivative of minus 1 over x squared, which is x to the minus 2, if you like. So the third derivative is 2 times x to the minus 3, because the minus signs cancel. Again, subbing in x is equal to 1 into this formula, we find that the third derivative is 2. And now we substitute this value into our general formula for the polynomial, and you get what you see at the bottom of the screen. Let's put it on our graph. This is a similar graph to before, in that the light gray parabola now is just the T2 polynomial, and the black curve now is the cubic polynomial T3. And again, you see the approximation of our logarithm gets better each time. So close to the point 1, 0, the cubic polynomial does a better job at approximating the function f of x, or logarithm of x. And now we can continue and continue and continue. So now, after 3 steps, it might be worth looking at a more general polynomial. Let's say we choose a polynomial of degree n, where n can be any number. So we choose a function f. In our example, f is the logarithm. We choose a point x equal to a. In our example, a is 1. And then we consider the following polynomial, Tn of x. This is very much built as we did in the example. So we start with f of a, then we add f prime of a over 1, okay, times x minus a, plus second derivative of f at a over 2, or 2 factorial, times x minus a squared, plus and so on, all the way up to n. So the last term in the polynomial is the nth derivative of f at the point a divided by n factorial, times x minus a to the n. So this might look a bit complicated, but if you go through it carefully, you will see in order to actually compute a value of Tn of x, all you need are the derivatives of f at the point a from 1 to n, and you need the function value f of a. So the only variable in this polynomial really is x, because a is a number that we choose beforehand. And when you look at the last term, you get x minus a to the n. So that's an x to the n, which means Tn is a polynomial of degree n. And what are the properties of Tn? Well, we've constructed Tn in the same way as in the example before. So we know that Tn and f agree in all derivatives up to order n at the point x is equal to a. And a polynomial with this property is called a Taylor polynomial. So Tn is the Taylor polynomial of degree n. And now let's have a look at some examples of Tn for slightly bigger n's. We've already looked at T1, T2, and T3. On this slide, you can see pictures of T4, T6, and T20. Let's start on the left with the graph of T4, again shown in black. The gray curve you see is the cubic polynomial we had before. And just like in the other cases, the approximation of the polynomial gets better and better the more we increase our number n, the degree of the polynomial. In the middle, you see the graph of T6, so the polynomial of degree 6. Again, an improvement in the approximation. And then, I didn't do this by hand, but I used the computer, but never mind. On the right-hand side, you see T20. So that's the polynomial of degree 20. And you can see that this does already a very good job at approximating the function. In fact, it very much looks like the function logarithm of x, at least close to the point 1, 0. You also see on the right-hand side, when x gets too big, around 2, then the polynomial moves away from the blue graph, so it doesn't have to do anything with our function anymore. But close to 1, 0, it does a very, very good job.